Thank you. So firstly, I'd like to thank Professor Yungjin So for giving me this chance to have a talk here. So about 3 years ago, I visited here as a postdoc fellow. Professor So is my supervisor at that time. So thanks him again. So today, I'll give the talk. The title of my talk is Eigenvalues of the Jacobi operator and the index for hypersurfaces in a sphere. So my talk has 3 parts. In the first part, I will give some introduction, and the second part, I will talk about the eigenvalues of Jacobi operator for the hypersurfaces with constant mean curvature, all the hypersurfaces with constant scalar curvature. And in the last, in the third section, I'll introduce the weak stability Jacobi weak stability index. So now let's begin. Now the first part. So I'll give some introduction. If M is a n-dimensional complete hypersurfaces in a unit sphere, then for any smooth function f, let Fij denotes its Hessian. We can firstly we can define this differential operator. The Laplacian is defined by this one. So next, I introduced the second operator. This box operator is defined by this one. So this box f equal to this one. In h, the delta h, here the h means the mean curvature of the M. So where Hij denotes the components of the second fundamental form. So from this definition, we know that for the compact hypersurfaces, this operator, this differential operator is self-adjoint. So this operator, this differential operator was introduced by and used by the Professor Zheng and Yao to study the compact hypersurfaces with constant scalar curvature in a unit sphere. In fact, they proved the following result. This result: if M is an n-dimensional compact hypersurfaces with constant scalar curvature, here the n, the times n minus 1 times r, the small r isn't less than 1, and if the sectional curvature of M is non-negative, and then we can get that M is a totally umbilical hypersurfaces. This means that M is a sphere. Or a Clifford hypersurfaces. This Clifford hypersurface means the Riemann product. Here the C means a sphere of the radius C. C denotes the radius. So this is and Professor Zheng and Yao using this operator, this differential operator, and make using of this operator is self-adjoint. So they can get this result. So the first, this is the first 2 operators. So next, I give the M's mean curvature HM. This is the definition. The M's the high order mean curvature. This is the high order mean curvature. The M's mean curvature HM of the hypersurfaces M is defined by the following. It's defined to be the elementary symmetric polynomial of the degree M in the principal curvatures K1, Kn. Here K1, K2, Kn are the principal curvatures of the hypersurfaces M. So here HM is defined by this formula. Here the SM, from here we can get the definition of the SM. Here the capital C NM is a combination number. So from this definition, we know that if here, m equal to 1, here m equal to 1, we can get that this is the h1. h1 is equal to the m equal to the h. Here h means the mean curvature of hypersurfaces. So here the h equal to this one. So this is the mean curvature. If the h here m is equal to 2, and we can by the Gaussian equation, if the m is the hypersurfaces in a unit sphere, then by the Gaussian equation we can get the scalar curvature r is equal to this one, is equal to this one. So of course we can get the other relationships between the hm and the some of the terms. So here here we compute the Gauss Kronig curvature k. Here the capital K equal to the k1, the product the kn. This is the Gauss Kronig curvature. This is equal to the hn. So this is the definition about the high order mean curvature hm. And the Professor Cho also proved some of the theorem about the m's mean curvature hm. For the Euclidean space, if the mean curvature is h is constant and the m's mean curvature constant, then he proved that the m is a hypersphere. So this is the definition of the high order mean curvature hm. So next is in the second section, I'll introduce the eigenvalues of the Jacobi operator and the index. In the first subsection, I'll try to give the introduction about the hypersurfaces with constant mean curvature. If m is an n-dimensional compact hypersurfaces in a unit sphere, then we can compute the first variation. Here the Vt, the capital Vt, is a volume functional. By the compute the first variation, we can get the Euler-Lagrange equation. Here the Euler-Lagrange equation means the h equal to 0. So if h equal to 0, we coin m is minimal hypersurfaces. So if we restrict here, so here minimal hypersurfaces are characterized as the critical points of the volume functional Vt. Here, sorry, here the Vt, capital Vt, means the volume functional. So if we restrict the variation Vt such that this variation preserved, such that this variations preserved preserved preserve a volume function, that means the integral of the u equal to 0. Thank you very much. Thank you. sorry. So we can get the Euler-Lagrange equation, means the h, the capital H, here the mean curvature h equal to constant. This means the constant mean curvature hypersurfaces can be viewed as the critical points of the volume functional. Here, the variation restricted to the variation that preserved a certain volume function. So this is about the first variation. We can continue to compute the second variation of this functional, volume functional, and we can get for this we can compute the second variation of the volume functional, and here we compute the second variation is given by this one. Here the capital Jm is equal to the minus the negative the Laplacian, the minus the s minus n. Here n is the dimension of the hypersurfaces. So here is the Laplace and S denotes the squared normal of the second fundamental form of M. Here the Jm is called a Jacobi operator or stability operator, since this operator is related to the stability of the hypersurfaces. So we call this operator Jm is a stability operator. Stability operator. So in fact, about the first eigenvalue of the Laplacian, we know that the Yao proposed the following conjecture, this conjecture. So he proposed that the first eigenvalue of the Laplacian on a compact embedded minimal hypersurfaces in a unit sphere is equal to n. So for this conjecture, the Korean geometer made an important development. They proved that this is not less than n over 2. So this is about the first eigenvalue of the Laplacian. So now we want to consider the first variation, first eigenvalue of this operator, of the Jacobi operator. This the Yau's conjecture is about the eigenvalue of the Laplacian operator. So next we consider the first eigenvalue of the Jacobi operator of the minimal hypersurfaces in a unit sphere. About this, the first eigenvalue of the Jacobi operator of the minimal hypersurfaces in a unit sphere was considered by the GSMs, the Chuanxiwu and the Paidong, and then give the characterization of the Clifford torus. So by the first eigenvalue of the Jacobi operator, the Gm. So in fact, they proved the following results. These results. They said that if the M is an n-dimensional compact minimal hypersurfaces in a unit sphere, then the first eigenvalue of the Jacobi operator Gm satisfied these results. The first result is the first eigenvalue of the Jacobi operator Gm is equal to the negative n, and here M is totally geodesic. Means M is a sphere. So the second result said that the first eigenvalue of this Jacobi operator is not greater than negative 2n here in the dimensional of the hypersurfaces M. So if this equality holds, if and only if M is a Clifford minimal torus. So this is the first eigenvalue of the Jacobi operator of the minimal hypersurfaces in a unit sphere. So if for the mean curvature hypersurfaces, the Alias, Barros, and the Brazil proved this result. If M is an n-dimensional compact hypersurfaces with a constant mean curvature, means that the h, the capital H, is equal to the constant. So in this case, they proved the first eigenvalue of the Jacobi operator satisfied the first satisfied the following. So the first one is the first eigenvalue of this Jacobi operator is equal to the negative n, the times 1 plus h square. Here M is a totally umbilical. So from here we can know that if h equal to 0 means the M is the minimal hypersurfaces, then the first eigenvalue of Jacobi operator is equal to the negative n. So the first one. So the second, give that the first eigenvalue of Jacobi operator satisfied this inequality. Here the capital here the S denotes the squared normal of the second fundamental form. H means mean curvature. So H means mean curvature. So if this equality becoming the equality if and only if M is a Clifford hypersurfaces. From this result, we know that if the special case, if the h equal to 0, special case, if h equal to 0, and this results reduce the two results of the GSM's results. So this is about the first eigenvalue of the Jacobi operator. So now we will study the second eigenvalue of this Jacobi operator. So now we introduced some results about the second eigenvalue of the Jacobi operator. For compact hypersurfaces with constant mean curvature in a unit sphere, Sophie and Alias proved this result. The second eigenvalue of the Jacobi operator satisfied this equation. So here means the second eigenvalue of the Jacobi operator is non-positive. If this is the second eigenvalue of the Jacobi operator is equal to 0, if and only if M is totally umbilical. So this is the Sophie and the Alias results. So this is about the second eigenvalue of the Jacobi operator. So now we introduced some of the definition. We know that this Jacobi operator induced the quadratic form, this quadratic form, the QM, this quadratic form, the acting on the space of the smooth function on M, this space. So in this case, in the case of the constant mean curvature, in this case, we give the definition, the index of a constant mean curvature hypersurfaces. Index is defined as the maximum dimension of the subspace of the space of the smooth functions on M, on which this quadratic form is negative definite. So from this definition and the quadratic form, the QM, we know that this index means that the number of the non-negative eigenvalues of the Jacobi operator. So if we want to compute the index of hypersurfaces, we only need to compute the negative eigenvalues of this Jacobi operator. So if we want to estimate the eigenvalue of the Jacobi operator, we can using the min-max principle. To compute to give an estimate. So this is the definition. From this definition and the above the theorems, we can get the first the corollary due to the GSMs. So if M is a compact, the minimal hypersurfaces in a unit sphere, then we know that the index is not less than 1. Further, if the dimension, if the index equal to 1, if and only if M is totally geodesic. So this is the first result. So the second one, due to the Sophie and Alias, if M is a compact hypersurfaces with a constant mean curvature, then we know that we can get the index is greater than and equal to the 1, and the index is equal to 1 if and only if M is totally umbilical. If M is a compact non-totally umbilical hypersurfaces with a constant mean curvature, then we know we can obtain the index of M is greater than and equal to the 2. So next the Professor Padon proved if the M is a compact non-totally geodesic minimal hypersurfaces in a unit sphere, then the index is greater than and equal to the n plus 3. So this is the Padum's result. So now I'll introduce the Professor Fabiano Urbano's result. If M is a minimal surface in a unit sphere of dimension 3, and the index equal to 5, then M is a Clifford torus. So since the Professor Urbano proved this result by using the Gauss-Bonnier theorem and construct some function, some conformal transformation to prove these results. So, so on the other hand, we know that we can compute the index of the Clifford torus. So by a direct calculation, we know that the minimal Clifford hypersurfaces, this means the Clifford torus satisfied the index equal to the n plus 3. So we proposed the following conjecture. The first conjecture. So the only minimal hypersurfaces in a unit sphere with the dimension with the index of the hypersurfaces is equal to the n plus 3 are the minimal Clifford hypersurfaces, means the Clifford torus. So before we propose the following conjecture, I'd like to introduce this results. This result said that if M is a compact, the n-dimensional minimal hypersurfaces in a unit sphere, if the index of the M is greater than and equal to the n plus 3, then we can get this inequality. Here, the capital S, denotes the squared normal of the second fundamental form here. So, moreover, if the integral of the S is equal to the integral of the n, then M must be the isometric to a minimal Clifford hypersurfaces, means the Clifford torus. So from the SS Chen and Ducam Kobayashi's results, we know that if the square normal of the second fundamental form S is equal to n for the minimal hypersurfaces, we know that this hypersurfaces is a Clifford torus. So by this example, by computing the index of the Clifford torus and Professor Urbano's results, so we proposed this conjecture. So from the Urbano's results, we know that this conjecture is true for the dimension n is equal to 2 for the surfaces.
Excuse me. What is the integration n? N is a dimensional n?
Here, the n.
N.
You mean here? N is the dimension of the hypersurfaces.
Okay.
So from the Urbano's results, we know that for the minimal surfaces, if the index equal to the 5 means the 3, means the n plus 3. Here n is equal to 2, right? Hypersurfaces. So for this special case, for the minimal surfaces, this conjecture is true. Means if the n equal to 2, here the index is equal to 5, and then the minimal hypersurfaces satisfy this equation as the minimal Clifford hypersurfaces. So from the Urbano's results, we know that this conjecture is true. So now I'd like to give another conjecture. If M is a compact, the non-totally umbilical hypersurfaces, non-totally umbilical hypersurfaces with constant mean curvature, then we propose we guess that the index is greater than and equal to the n plus 3 for the constant mean curvature. Here is for the minimal hypersurfaces, for compact non-totally umbilical hypersurfaces. So this is about the hypersurfaces with constant mean curvature. Now I'll introduce the hypersurfaces with constant scalar curvature. So for the hypersurfaces with constant scalar curvature, I'll introduce the eigenvalues of the Jacobi operator and the index. So we know that for this functional, we can compute the first variation of this functional, and we can get the Euler Lagrange equation. Euler Lagrange equation means the capital R equal to the constant. Here, the capital R is the scalar curvature of the hypersurfaces. So for this volume preserved the variation means the integral of ut equal to 0. So this is the first variation. We can continue to compute the second variation of this functional, and we can get that the Js here, the capital Js means the Js equal to this one. Here, this is the box operator. Box operator was considered by Professor Zheng and Yang. So the Js here, the F3 equal to this one. The Ki means that the principal curvature of the M. Here, the S means the squared norm of the second fundamental form. So from here, the Js also coined the Jacobi operator. So by the definition, and we can prove that for if the scalar curvature R is greater than n times a minus 1, then we know that this operator is elliptic. If we know that this operator is elliptic, we can use the minimax principle to compute its eigenvalues. So this is Jacobi operator for the hypersurfaces with constant scalar curvature in a unit sphere. So now recently, Professor Chen has studied the first eigenvalue of the Jacobi operator of hypersurfaces with constant scalar curvature n times n minus 1 r. Here the small r is greater than 1 in a unit sphere, and then he proved the following: if M is an n-dimensional compact hypersurfaces with constant scalar curvature, here the R is greater than 1 in the unit sphere, then this Jacobi operator is elliptic, and the first eigenvalue of this Jacobi operator satisfied this one. The first eigenvalue of Jacobi operator isn't greater than the negative n times n minus 1, the R, the square root, the R, the minus 1. And if this equality holds, if and only if M is totally umbilical and the non-totally geodesic. So this is about the first. This result is about the first eigenvalue of the Jacobi operator of hypersurfaces with constant scalar curvature. So similarly, we can consider the second eigenvalue of this Jacobi operator. We can consider the second eigenvalue of this Jacobi operator. So we proved about the second eigenvalue of this Jacobi operator. Chen and I proved this result. For the dimension n is greater than 4, let M is be n-dimensional compact hypersurfaces with constant scalar curvature R. With scalar curvature R, here in a unit sphere, then we know from here, using the Gaussian equation, we know that the mean curvature h isn't equal to 0 on M. So we can assume that the mean curvature h is positive. So and the second eigenvalue of this Jacobi operator, satisfied this equation. Means that the second eigenvalue of this Jacobi operator is a non-positive. Here the capital V denotes the volume of the M. Here the small r means this one, small r. Here the h is the mean curvature. The s the squared normal of the second fundamental form. If the second eigenvalue of Jacobi operator equal to 0, if and only if M is totally umbilical. So now next I'll give the proof of these results. So question for, if we want to prove this result, it's important for us to find the test function. So the question, how to choose the test function f? How to choose the test function f? That means that here, since in this theorem we want to compute the second eigenvalue. So that is to say, if rho is a first eigenfunction of the Jacobi operator, then we must find the test function f such that the integral of the rho and f equal to 0 according to the minimax principle. So we should find the test function f satisfied this equation. So the following, the method is the following. So at the first, we introduced the conformal, the transformation from a sphere to a sphere. So this conformal transformation was introduced by Li and Yao, Peter Li and St. Yao. So if for this open unit ball in a Euclidean space, for each point x, we can consider this map. So this map. Here the P belongs to the unit sphere. Here P belongs to a unit sphere. So the lambda equal to this one. Here x is the point of this unit ball. So lambda equal to this one, and mu satisfied this equation. And a direct calculation showing that this map is a conformal transformation from the unit sphere to a unit sphere. Since this map is a conformal transformation, so we can write this metric. This metric is equal to the pullback of the H0. Equal to H0. Since this map is a conformal transformation, so we know that the H tilde equal to the EF, the H0. Here the EF. If the EF isn't equal to 1, so this means the conformal transformation. If the EF equal to 1, this means the remaining manifold. So moreover, for any tangent vector, we can compute this one, and we can get the differential, the d, the ix v and dix w is equal to this one. So this means the inner product. So next, I give the following lemma, the Li and Yao's lemma. If the G is a Riemann metric on M and the phi from M to the unit sphere, is a conformal emerging. Conformal emerging. Conformal emerging means that the pullback edge means that means this one. Conformal transformation. So is equal conformal emerging, then there exists the point x that belong to the open unit ball, such that the integral of this term is equal to 0. So from this lemma, they supplied us a method to prove our results. So here, since the small r is greater than 1, we know that the Jacobi operator is elliptic. In fact, from the Gaussian equation, we can get the n square, h square, the greater than the squared normal of the second fundamental form. Since the square normal of the second fundamental form is equal to the sum of the principal curvature square, so S is greater than and equal to the Ki square. This is non-negative. So from here we can assume the H equal to mean curvature is positive and NH is greater than Ki, and from the definition of the box operator, we can prove that this operator is elliptic. So if rho is a first eigenfunction of the Jacobi operator, we can assume that this eigenfunction is positive. Then we can consider the remaining manifold, with the metric, with this metric. So since this map is a conformal map, so by the Lee and Yau's lemma, we know in this equation. Here the metric, this is a metric. Here this is a manifold M metric. So on the other hand, we know that the D, so the metric, the element of the volume satisfied some of the equation, some of the relationship. So here this term is equal to this term. So with the rho, here the rho is this one. So from here we can, from this equation, we know that if we assume that the capital Xi equal to this one, so, here the epsilon 1 equal to this one, and the epsilon n plus 2 equal to this one. So from this equation and this equation, we can get this. We can get this following equation. So here, from here, we know that rho is a first eigenfunction of the Jacobi operator. The rho, the capital Xi equal to this one. So from this function, this equation means that the first eigenfunction of Jacobi operator and the capital Xi are orthogonal. So from the minimax principle, we know that the Xi is a test function. So we found the test function, the capital Xi. So from the minimax principle, we can get the second eigenfunction of the Jacobi operator satisfied this equation. And summing up and using the factor that the capital Xi equal to 1, since the Xi, so since the image is in the unit sphere, so capital Xi square satisfied this equation. So by using this equation and the Stokes formula, the conformal scalar curvature equation, and this algebra lemma, we can prove our theorem. Our theorem. So this is about the second part of my talk. Now I'll give the last part of my talk. So So sorry. Sorry. Before I continue to introduce the finally part of my talk, I'll introduce some of the definition of the index.
Excuse me.
Yeah.
Why do you assume rho is always positive? First eigenfunction.
Since the
always positive function.
Yes, rho is the first eigenfunction. So we can assume that the first eigenfunction is always positive. If the rho isn't the positive, then you can find this. If you want to find the test function, since for the first eigenvalue, for the first eigenfunction, we know that the first eigenvalue function is always positive. So here we assume that the rho is positive. Then we try to find the sum of the test function such that the first eigenfunction and the test function are orthogonal. So for this Jacobi operator, induced the quadratic form. This quadratic form. So this the space means the space of the smooth function on M. So in the case of the hypersurfaces with constant scalar curvature, the index is defined by this way. Here the quadratic form, the Q, means equal to this one. So from this definition, we know that the index is equal to the number of the negative eigenfunction of this Jacobi operator, the GS. So from this definition, we know that our results can be rewrote the following. So this means the index is greater than and equal to the 1. If this index is equal to 1, if and only if M is totally umbilical. So next I introduced the weak stability index, not the stability index, the weak stability index. So the weak stability index means that the Jacobi operator also induced the quadratic form here, but this quadratic form acting on this space. This space is a subspace of the space of smooth function on M. This means this space satisfied the integral of the U equal to 0. So the different. So here we give the definition. The weak stability index. Weak stability index means that the maximum dimensional of any submanifold V of this space, the C T infinity means this one, on which the quadratic form is a negative definite. Well, here this the space, the C, and the quadratic form Q, just like this. So now we can compute some special hypersurfaces, the index. So if M is a totally umbilical hypersurfaces of a unit sphere, then we can compute. We can get that the weak here, the T means here the we call it the weak stability index. Here the weak stability index of the total umbilical hypersurfaces is equal to 0. So another simple example is about the Clifford hypersurfaces. Now we compute the Clifford hypersurfaces, the weak stability index. So we'll compute the weak stability index of the Clifford hypersurfaces. So by a direct calculation, we know that the principal curvature are given by this equation. So we can, by the Gauss equation, we can get this the mean curvature is positive if and only if the C square satisfied this inequality. So it followed that the Jacobi operator, the JS, becoming this one. So next we try to compute the eigenvalue of this Jacobi operator. Means at the first we showed compute the eigenvalue of the box operator. So we can get we can obtain. We have the eigenvalue of the Jacobi operator are given by this one. This means the eigenvalue of the operator box operator. That relationship. This is expressed that relationship between the the eigenvalue of this Jacobi operator and the eigenvalue of the box operator. So therefore we have this one. Here the Laplace one means the first eigenvalue of the Laplacian. This is the second. So by a direct computation, we obtained the weak stability index of the Clifford torus isn't less than n plus 2. Isn't less than n plus 2. Here we assume that the r, the small r, is greater than 1. Moreover, if the weak stability index is equal to n plus 2, if and only if the c square satisfied this equation. So here we also point out the following interesting factor. This factor. So on the weak stability index of Clifford hypersurfaces, so the weak stability index approached to infinity if as the c square approached to 1. And we can get the weak stability index approach to the infinity. Here. This is the first factor. The second factor is that the weak stability is equal to the index of the weak stability is equal to the index of the stability minus 1 for the Clifford hypersurfaces. So there exist the two factors about the Clifford hypersurfaces. So now we give some of the results about the weak stability index. So here for the hypersurfaces with constant scalar curvature, if the M is a compact hypersurfaces in a unit sphere and unit sphere with constant scalar curvature, if the H1 and H3 are constants, then we can get that the weak stability index equal to 0. In this case, the M is a totally umbilical. So all the weak stability index isn't less than n plus 2. If the equality holds, if and only if M is a Clifford hypersurfaces. So this is the first result. So the second one said that if M is a compact hypersurfaces in a unit sphere with constant scalar curvature, but here we restrict R. The R is greater than 1, and R isn't equal to these numbers. So if we assume that the H1 and the H3 are constants, then M is a totally umbilical, or the M is a Clifford hypersurfaces, or the weak stability index of M isn't less than 2n plus 4. So here is the second result. Now I'd like to give the brief of our results. So in order to prove our theorem, we should introduce the two functions. Since we want to find the eigenfunctions, so we introduced the two functions, the RW and FW. Here, for the arbitrary vector W, we defined the functions, the RW and FW, as follows. This one. Here, the psi means the emerging from the M to the unit sphere. Here, the nu means the normal vector, normal vector. So by a direct calculation, we can get the second the Jacobi operator RV equal to this one. So this is the Jacobi operator JS FV equal to this one. Here the S1 S2 is defined by the M's mean curvature. So we ideal I talk about the idea of this theorem. So we try to find the sum of the alpha is a real number such that the functions, the fv, the plus the alpha rv are the eigenfunctions of the GS. So the idea is that we try to find the sum of the eigenfunctions of this Jacobi operator. This Jacobi operator. So that means this one. That means this one. So moreover, we also need the following the inequalities. This inequality, the h1 square, the greater than is less than the h2, and this one. So then we can prove our theorem. So next, by the investigating and the proportion relationship between the RW and the FW, this the result. So this result means if M is a compact, is a complete, here the complete, not compact, complete Riemann manifold with the constant scalar curvature, here the R isn't equal to these numbers. If the RV and FV satisfy this relationship, and then we can get the phi M is either a totally umbilical sphere or a Clifford hypersurfaces. So if this theorem means that for the hypersurfaces with constant scalar curvature, if the RV and FV satisfy this one, and then phi M is a totally umbilical sphere or a Clifford hypersurfaces. So if M is a totally umbilical sphere, not a Clifford hypersurfaces, we obtained from the theorem that this one. So for any fixed vector, then from the proof of the theorem 3.1, one has this relationship. This is the equality. So next, by the consider the proportional relationship between the RW and FW, and using the similar arguments in the proof of the theorem, we proved this result. So here the M is a complete Riemann manifold with the constant the radius of the Gauss-Kronecker curvature and the n-1 the mean curvature means this one. And in addition, the RV equal to the lambda FV, then the phi M is either a totally umbilical sphere or a Clifford hypersurfaces. So the two conditions. The first is about the Sn equal to the C Sn minus 1. The second condition is that the RV equal to the lambda FV. Then we can get the M is a totally umbilical sphere or a Clifford hypersurfaces. So the last result is about if M is a compact hypersurface, is a complete hypersurfaces with a constant Gauss-Kronecker curvature C. Means the Gauss-Kronecker curvature C is a constant. Here the C isn't equal to the 1 or negative 1. If the RV equal to the lambda FV, then we can get the phi M is either a totally umbilical sphere, not a Clifford hypersurfaces. So maybe you will ask one question: are there examples such that if the RV equal to the lambda FV and the Gauss-Kronecker curvature C isn't equal to constant? So finally, I give the example about to explain this question. So we'll give some of the non-trivial examples M which satisfies RV and equal to the FV. RV equal to FV. So for the V, vector V, for a fixed unit vector and C a real number, then we define this the Sn. For we assume that the E1 equal to the 1, 0, 0. So the C equal to the 4 over 5. Then we know that the Sn is a sphere, and we can compute its principal curvature. is equal to the 4 over 3. So we by the producing this sphere, by producing this sphere, so we can find a hypersurface the n, whose mean curvature isn't constant, and such that all the principal curvature lambda I is greater than 1 and less than 2. So here, since the 4 over 3 satisfied this equation, this inequality, so let m equal to this one. So here the n, this is the n, the capital N, and phi we define this the emerging, the phi from m to the unit sphere given by this equation, given by this one. So here the s is a parametrics of the S1. Here x belongs to the capital N. So we give this emerging, and from this emerging, we can get that the V1, Vn minus 1 is a basis of a tangent space of N, such that this equation. So from this relationship, if we assume that the V1 equal to and Vn minus 2 equal to this one, then we can compute the d psi and d psi. We can compute the d psi. So from here we know that the d psi isn't equal to 0 if the d psi isn't equal to 0, means that the psi is emerging, means emerging. So here, from here, you know this isn't equal to 0. This term isn't equal to 0. So this isn't equal to 0. So we can get the psi is emerging, and moreover, we can compute the V tutor from M to a unit sphere given by this one is a Gauss map. Using the expression for the phi and the V tutor, we get that the RV and the FV satisfied this relationship. So from here we can get that this manifold M, this emerging, this M, this is the hypersurface M in a unit sphere. So its Gauss canonical curvature isn't equal to 0, and the scalar curvature isn't equal to 0. So moreover, the Gauss canonical curvature and n minus 1, the mean curvature of the radius isn't equal to 0. So from this example, we know that there exists some non-trivial example satisfied the LV and FV equal to the FV, satisfied LV and equal to the lambda FV, and M isn't the trivial example. So this example told that our theorem is there exists some example do not satisfy the M is not a constant Gauss canonical curvature, but the RV and FV satisfied this equation. So today I'll stop here. Oh, thank you very much.
Any question or comment? So you